All right, talking about blade element theory. Oh, here we go. So point number 3 on blade element theory, and I got a little wordy, sorry. Theory states that the many airfoil sections or the elements are formed together to create an airfoil. So we basically just took a blade and we slice it up into 1-inch sections and said, hey, look, they're all different. Now we put them back together and it creates a propeller, which is kind of a silly thing to do, but that's what we just did, right? So each theory states that the many airfoil sections, or elements, because it's the blade element theory, are formed together to create an airfoil. That can create thrust when rotated around a central hub or plane, central plane.
What do you mean axis? Okay.
It's the book I got it out called the central plane. So if they wanted to call it, I'm sticking with it, right or wrong. All right, so this point is somewhat important. Each element is designed to operate at its best angle of attack. Angle of attack can be abbreviated angle of attack. Since each section or element moves at a different speed. All right, so where I'm going to go with this, what I'm going to show you is exactly why it's this way. All right, but remember that each element is shaped differently. Each element has a different angle to it, because as the propeller is going to spin around, each section of the propeller is really going to have a different angle of attack at the air coming at it. And if you change that angle of attack, then you're going to change the effectiveness of the propeller. So like, what's that, Sarah? Central, sorry. I know, central. All right, so each, unlike a wing, like a wing going forward, it more or less has the same angle of attack, unless the wing has a little bit of twist. And does a wing have a little bit of twist to it?
Yeah.
What do we call that?
Washing.
Wash in, wash out. So it depends. If you wash in a wing, you... No, I didn't know you were going to ask me this today. If you wash in a wing, you increase the angle of attack. If you wash out a wing, you decrease the angle of attack. So a wing and the outboard section, is it washed in or washed out? Washed out. So the inboard has more angle of incidence so that it stalls near the root first, right? All right, so back to this. So the same thing. Not that we want it to stall one section first, but it's the way it goes. Let's see, what point am I at? Did that one? Oh, here we go. Each section may have a different chord, thickness, and angle. Each section may have a different chord, And what is the chord?
Leading edge to trailing edge.
Leading edge, trailing edge. Different chord, thickness. And or angle. Which angle? Blade angle. Now remember, angle of attack is relative to what? Okay, the air coming at it. All right, tips. Tips move much faster than the hub. Now in revolutions per minute, it's all the same. But in actual speed, miles per hour, inches per minute, however you want to look at it, tips are moving a whole lot faster. I should write this note that the RPM is the same. So don't confuse revolutions per minute with actual speed as in miles per hour. The gradual change in blade sections, this slight changing over it, is called pitch distribution. So the gradual change in blade sections, or section angles, we'll say section angles. Is called what? There you go. Called pitch distribution. And that gives you that noticeable twist in the blade. So pitch distribution is the noticeable twist. All right, so we learned about the blade element theory, the pitch distribution. We know that the chord thickness and angles are all going to be different in each section going all the way down the propeller blade. We'll stop here. We'll talk a little about thrust. According to your Q&A, which is, I suppose, all that really matters when you're trying to pass the test. Thrust is produced by a rotating propeller in the same way lift is produced by a wing. And how is lift produced by a wing? You guys do remember this, right?
Bernoulli?
Don't make me go tell Phil you guys don't remember. So Bernoulli, what did Bernoulli say?
Going into a convergent duct, it increases in velocity but decreases in pressure.
Okay, so translate that into a wing for me.
In other words, the air going on the bottom part of the wing is slower and produces more pressure on the bottom of the wing than the faster over the top, so it actually sucks the wing up.
Okay, so according to Bernoulli's principle, is there actually a higher pressure under the wing?
Yes.
As opposed to the ambient air around it? Or is that ambient air?
That's ambient air. There's lower pressure on top of the wing.
Okay, so the bottom of the wing is pretty much just ambient, and the top is
Lower pressure.
lower, so the wing is
being sucked up.
in the air. All right, so according to this Q&A, it's the same thing. So that would mean then, if the base of the propeller is The flat part, the face of the propeller, the part towards the pilot, is that like the top of the wing or the bottom of the wing? I'm hearing bottom, which is good. Okay, bottom of the wing. And so the top of the wing is the, what is that called on the, is the back or the curved part, which is out front. So then how is the propeller creating thrust?
Low pressure on the back and it's ambient on the face part. So instead of like lift, it's going to go forward.
Okay, so, and very well. So, in other words, the propeller going through the air is creating a low pressure side on the front, so it's actually sucking the airplane forward. So that's, notice I put a coordinate Q&A. So thrust is produced by rotating propeller in the same way lift is produced by a wing. Whereas an area of decreased pressure is produced immediately in front of the propeller. An area of decreased pressure is produced immediately and then the second point to that is then aerodynamic. Aerodynamic forces cause the propeller to move into this area of low pressure. Just like a wing then is sucked up, it is caused to move into this area of low pressure. So aerodynamic forces cause propeller to move into this area of low pressure. All right. Anybody have a problem with this definition there? Yes. Why do you have a problem with this? What's that? He's saying Newton is excluded. I don't like him anyway. He wasn't at the convention.
We voted him out.
Prince is right. If we do that, then we're excluding Newton. Remember what I told you too. Yeah. Did I tell you guys? Depends on what you had for 309. But we talked about in 309, I think what I did, aerodynamics, that, you know, not that long ago when I was in A&P school, it was only Bernoulli. And there was no other theory at all in flight. And when I had read the Stick and Rudder by Wolfgang Logenstein, is that correct? That he introduced introduced Newton's theory into it. And at the time I read it and I talked to pilots, I said, man, you need to throw away that cult book or whatever it is you're reading there because that's just hogwash. Well, now it's just common knowledge and it hasn't been that long ago. All right, so some textbooks, give credit here. Some textbooks add Newton's third law. And which law? What is Newton's third law?
For every action, there's an equal and opposite reaction.
For every action, there is an equal and opposite reaction. Not to be confused with Murphy's third law. Hey, you guys, this is true. What did Murphy of Murphy's Law do for a living?
Oh, yes, I'm military, right?
Might have been military, but what did he actually do? He played Jesus? What?
Did he make pizzas?
You make pizzas? He was an aircraft mechanic. I kid you not. R-E-A-C-T.
I know Murphy's first law, whatever can go wrong will go wrong in the worst possible place.
There you go. And this was said by a aircraft mechanic. So, I'll have to look up exactly what he did, but I know that he was involved in aviation. There's an equal and opposite reaction. Where am I here? Let me see. Equal abstraction, and the two are directed along the same straight line. We don't need to do all that. Okay, so action 1. What is my action 1? So for every action, there's an equal and opposite reaction. So what is action 1?
Blade axon air.
Blade axon air. Okay, so we'll say acceleration of a mass of air. So the propeller is going to take this mass of air and accelerate it backwards, hopefully. Mass of air by the blade toward the rear of the plane. So if we move this mass of air, accelerate it towards the rear of the plane, and that's my action 1, then I must have action 2, or the reaction. Action 2. Oh, I'm going to throw one other point in here, so I'm just going to back up a little bit. And POA and plane. And my other point here that I should have made is, well, we could assume or pretend we have 200 pounds of air accelerated. So if that's my action 1, then I have action 2, or I could call it reaction. Reaction. The plane is pulled forward because it accelerated the air backwards, then the plane has to go forward. So the plane is pulled forward by with 200 pounds of force. So there's my action, there's my reaction. So how does a plane work? Just like a wing. Bernoulli and Newton.
Why was the question for so long?
Why is the what so long?
Why was the question for so long? If it's just if you can prove it just by like static thrust,
Yeah,
why was the question for so long?
I don't know. Sometimes you wonder if people really thought about it, if they just accepted it. It was the accepted norm, and then to buck it. I don't know. All right, let's talk about blade angles. Blade angles. All right, so I'm going to see slide 6, 4, 5, 6. All right, from current slide. This is a 4-bladed propeller. All right, so first thing you have to note is that. If you miss that, then you're going to miss the whole thing. So 4-bladed propeller. Got one blade going up, one blade going down. I have one hidden from view, and I have another one right here so that we can kind of take a look at the profile of the blade. I'm looking at the cord right here running through it. So, no, 4-blade propeller. Okay, blade face is the part that is flat and faces the pilot. Now, pilot's over here. And we're looking at the angle. So this is the angle of the blade. So it's in line with the longitudinal axis. So there's my blade angle. Follow that one? Yeah, we're good. Okay, blade angle. Blade angle. The definition, the angle between, anybody want to try that? Between what?
Plane of rotation.
Yep, very good. Between planar rotation and,
Chord angle.
there you go, good job. Between the chord. I'm going to say often the face, but not always. The reason why I want to say often the face is because the face of the blade is usually flat Even if it's not, sometimes it's concave, but it's concave in such a way that you can still put a protractor against it, and you can actually get a blade angle from the face. So if you're trying to set blade angles, which is something you guys will actually do, check blade angles and set blade angles, you'll do in this class, is you can't really put the protractor against the chord line, can you? If the chord line is running through the middle. It's kind of hard to do that, but because the blade is flat, it's often thought to be the same angle as the chord line. So you can just use the face for doing that. Definition: the angle between the chord, often the face, but not always, of a blade, of a particular blade section and the plane of rotation. Let's see. Oh, note Q&A states chord. Oops, chord. Your Q&A does state, use the word chord in there, so I don't want you to mix that up. Yes.
What is the plane of rotation?
That's the point the plane rotates around. No, that's not it. Okay. It's funny you should ask that, because I was sitting here thinking, how can I explain plane of rotation and how this really works? And then you said, what's plane of rotation?
I can kind of.
Go ahead. Then I'm going to do something too. Go ahead.
Okay, so if you have a square, like just a flat square in space, and you expand it infinitely in every direction, like a piece of paper, yeah, I guess. Then it's going to that is going to be your plane where it rotates in. It stays within that plane at all times. So it doesn't go out of that plane.
Okay, we've got that. This shows a plane of rotation here, but the point that it's actually making is that it's hinged, well, it runs through the center line here, and of course, stop it, this propeller is spinning around. So, okay, so like when we're running engines on the test stand, I say the one place I don't want to stand, and the propeller's spinning this way, where don't I want to stand? In line with the propeller. So if the propeller blade broke off, it goes that way. So if the propeller's spinning around this way, you are directly in the plane of rotation. So it's that disc, if you will. Okay? But that's all fine and well. How can you, as a mechanic, if you are going to measure the blade angle relative to the plane of rotation, you have to kind of think about the way this drawing is set. The longitudinal axis is perfectly horizontal. And that's awesome, it's perfectly horizontal. And so if I wanted to measure that, I could take a protractor and I could put it along here and figure out this blade angle between here and here. And that works with a bubble protractor as long as the longitudinal axis is perfectly considered 0 or at 90 degrees. But what happens if we're working on some sort of tail-wheeled airplane, or an airplane where the longitudinal axis is this way? Now we got a problem, because the plane of rotation is going to be, that didn't work out at all. I wanted to erase it. Plane of rotation is going to be still at an angle. Follow? All right. So one of the things that you have to consider when you're checking blade angle then is, now we get a blade angle that's tilted in a third direction. So the blade angle would be like that. Well, if I compare this blade angle that I just made with this longitudinal axis and this plane of rotation, then is this blade, it looks really flat, doesn't it? It's kind of nearing a very low angle of attack. And so I say, oh no, that one's a very low angle of attack, but it's not. I tried to draw it exactly the same as this one over here. So it has the same angle of attack over here, but yet it looks very flat. You guys follow me where I'm going with that? Or can you see how when you change the the aircraft and you put the tail down, how everything suddenly changes. Now, that's great. You're looking at it on this side. If I could draw really nice and I could turn this around and show you the other side, then it's going to get worse, but go the other way. So everything gets all kind of goofy because it's going to spin around. So what is flat on this way becomes not flat on the other side. And do you guys remember P factor? Please say yes. I'll go get Phil. I mean it. So what was P factor in an airplane? Descending.
Blade has a bigger angle of attack than the ascending blade has a bigger angle of attack than the descending blade.
Okay, so you have dissymmetry of attack on your blades, and it's going to cause a plane to go right or left. Left, because I put right input, so it's going to go left. So you have on the right side, it's pulling more, so making the plane go left. So where you started out straight and level, the right blade and the left blade, or the descending and the advancing blade, had equal angle of attack. And then the aircraft tilts forward, and that made the blades change, so one went flat and one took a big bite, right? Okay, the same, so you have to remember that's what's going on here, and that's what I'm talking about. Well, not only does this happen in flight, but if you're measuring the blade angles, it's going to happen even on a static. You take a propeller, put it perfectly horizontal, but the aircraft is tilted, you're going to have one blade is going to look like it's got a lot of angle of attack, and the other blade is going to be no angle of attack. Now, what happens if you're not a graduate of this school and you think, whoa, well, there's your problem. You have dissymmetry of blades. I shall make both blades match. And so you get out, and you can adjust these on a ground adjustable, and you guys will actually have this as a project. You loosen up the clamps, and you can adjust the blades independently. So you adjust one blade for, 6 degrees, and you adjust the other blade for 6 degrees, but the airplane is sitting back at 6 degrees, so you put 0 pitch in one side and 12 degrees in the other is effectively what you end up doing. And so as the prop goes around, you have one blade that has a nice bite to it no matter where it is, and the other blade that never has any, or something like that. Anyway, so make sure that you understand, number one, where your plane of rotation is in relation to the longitudinal axis. Plane of rotation should always be 90 degrees off the longitudinal axis, unless it's some weird propeller.
Even if the plane longitudinal axis is like this, won't the plane of rotation still be 90 degrees?
It's always 90 degrees too. This is always 90 degrees. 90 degrees. So I tell you all that to tell you that I will have some fun with you because the project that we have for the ground adjustable prop would not be fun if the longitudinal axis was perfectly horizontal. So it is not. It is at an angle, which means that you have to keep all that in mind. And if you keep it in mind, it's actually quite easy, and you just keep there's a trick to it. And we'll talk about the protractors that we use. But basically what you're going to do is you're going to put a protractor on a surface, and you're going to zero it out. And you're going to say that's 0. And then you take that same protractor and you're going to put it, should use a different color, against the blade. And it'll tell you the degrees because you zeroed it out on the longitudinal axis. It's not a problem. And the trick to it is when you put the protractor on something and you zero it out sitting this way and you put it up to the blade sitting this way, you're going to walk around the airplane and you're going to want to put it back on the blade this way, but you just messed it all up. Once you set up your protractor to read this way, and you put it on the blade right here, then when you walk around to the other side of the blade, you have to continue to hold it the same way. That's the only trick. So, but I'll grab it, and I'm going to go like that and go, well, you're way off. And you go, no, you got to turn it around. I'm like, oh, okay, just checking. So, all right. All right, plane of rotation, blade angles. To create thrust, a blade must be set. at a certain angle to the plane of rotation. I'm going to throw this in here, or longitudinal axis. Or longitudinal axis. Why? Because it's just 90 degrees off. So it's not like you have to set it the plane of rotation. You can set it the longitudinal axis, just knowing plane of rotation is 90 degrees off. Or longitudinal axis.
Kevin,
Yeah.
I don't know if it's done nowadays, but are there any engines or planes that use tilted engines? Like where the prop's a little bit downward facing or upward facing?
Yeah, I'm pretty sure. Yeah, well, there's still planes in manufacture that do that. I don't know if their current production planes are. But there are planes that do that. I cannot think of any aircraft offhand that has a ground adjustable prop that you can adjust that has
It
that.
has that, okay.
Offset right or left. But as far as up and down, I think it's still pretty much in line. Okay, well, yes,
Before you move on, can you go back to that picture?
this one?
Yeah.
Okay.
So if you find the longitudinal axis and you zero out with your protractor,
Yep, find the longitudinal axis and zero out the protractor.
you are, but the blade angle is calculated from the plane of rotation to chord line. So do you go to the longitudinal axis, zero it out, and then find the angle from there to the chord line, and then subtract that from 90 and get the other angle?
Actually, it's really easy. So protractors kind of looks, prop protractor. Well, instead of drawing a really crazy picture, how about I do this? Oh, are you kidding me? I don't have a picture of one. All right. Going back to my crazy picture. A prop protractor looks like this. All has three sides that are perfectly 90 degrees. And one side that is rounded. And there's a dial in here, and it turns around with a little bubble in here. So what you would do is you would turn this until this bubble is zero here. Okay. Thing is, though, you can take this and just slide it over, and if you put it against the longitudinal axis, it would also read zero. So in reality, we don't usually use the plane of rotation, or I don't use the plane of rotation because you can't find it. It's too difficult. But what you can find is the longitudinal axis. It's really easy to find. It is, give me some examples. What is the longitudinal axis of a plane? What is something on an aircraft that would be perfectly in line with the longitudinal axis?
Floorboard of the cockpit.
The what? Floorboard of the cockpit? Nah, they're usually slanted a little bit. But remember, what is this attached to? What's running right through here? Crankshaft. Okay, so what? Give me some things that I can use then. What's one? Yes, Tim, the crankshaft. If I were to pull the prop off and I could put this right here on the crankshaft, is that going to be in line with the longitudinal axis? Okay, that's the number one answer. Survey says number one answer right there. So pull the prop off. In fact, that's what I have you do now is I changed the project, and that teaches you two things. One, how to get a really good longitudinal axis, and two, how to take a prop off and on, and why you need a bucket. Okay, so yeah, just put the prop protractor there.
Do it in the field?
Uh-huh. You can sometimes take off the spinner. Well, a ground adjustable doesn't have a dome like that on it. This is a constant speed. You can also cheat and put it against the front of the crankshaft, but you have to really hope that that's not messed up. So you're taking a chance there. How about the backbone of the engine? So top of the engine is usually in line. Not always. Some parts are angled, but there are places. But best answer, top of the crankshaft. All right, something about while. While what? While rotating in flight. While rotating flight, each section of the blade has a motion that combines the forward movement of the airplane with the rotary movement of the propeller. So it's two things are happening. One, the propeller is going around, and two, it's going forward. And so around. So if I'm stopped and my feet are on the brakes and the propeller is going around just like this, it's really easy to figure the angle of attack. It's coming around, and the air is not moving in any way, shape, or form. So the angle of attack is exactly where the propeller is coming down and striking the air. Follow? Okay, but now if I go forward, I have it striking the air, coming down, and whatever forward momentum I have. So those two things are now going to work together, harmoniously, to create problems. So we're rotating in flight. Each section of the blade has a motion that combines the forward movement of the airplane with the rotary movement of propeller. Of the prop. I'm going to skip forward just a little bit. I'm going to come back around to this one. But just to let you know where we're going, and you can kind of see this point. So here's, let's see, example 1, 2, 3, 1200 RPM, 1200 RPM, 1500 RPM. So the difference between 1 and 2, exact same RPM, this aircraft is sitting on the ground with the brakes, and it's not going anywhere. And what's my angle of attack? 20 degrees. Now, what you've learned from aerodynamics, is that a good angle of attack to have for a wing? What do I want for a wing, a good angle of attack? About how many degrees?
Less than 10.
Less than 10. About around 2, okay? 1 or 2, somewhere in that neighborhood. So how efficient is this propeller at 1200 RPM with the aircraft not moving? And it's 20 degrees angle of attack. Not very good at all. But take your feet off the brakes and let the aircraft start rolling down the runway at 50 miles an hour. That's a point. So 0.8 angle of attack. Is that a good angle of attack? Is this propeller being efficient? It's very efficient. So look at the change between being highly inefficient to being extremely efficient was the difference between standing still and moving forward at 50 miles per hour. Nothing else changed but forward movement of the aircraft, and the angle of attack changed by 21 degrees, close to 21 degrees. All right, and now take it one step further. The difference between example 2 and example 3, the speed has stayed the same, but the RPM was increased by 300 RPM. Angle of attack changed from 0.8 to 4.4. Only by 300 RPM. That's it. So you follow that? And so look at, I mean, if you really stop and think about, and if I only changed by 50, well, it's a big change, but 50 miles an hour, and I went from terribly inefficient to somewhere in the efficiency range, then I only added 300 RPM, and I changed the angle of attack by several degrees, you can see now that a fixed pitch propeller is really only efficient in a very, very narrow range of operation. Extremely narrow. Yes?
How is this
Relevant?
calculate the angle of attack?
I'm glad you asked. Pythagorean's theorem. I'll show you in a minute. And you're like, oh, I wish you wouldn't have.
How fast do you have to be going in an aircraft to actually create enough lift to take off? Pythagoras.
How fast do you have to be going in an aircraft to create lift to take off? This is your cue. Super fast. Depends on the airplane.
Okay.
Now, if you think about it, an airplane, like a Cub or something, 60, 40, 60? Okay. But if you have something that's an airplane, I don't know. What do you think, Jonathan?
25.
What's for Paul?
25.
25.
Sorry about your rap, 50.
No, because I saw a really cool meme today. Did you guys see that? Somebody posted. Guy and a girl sitting there having lunch, and you can tell he's trying to impress her, and there's a C-130 taking off in the background. It's like, so what do you fly? I said, see that right there? That's a C-130. I fly a C-150. That's right.
Somebody should make that as a poster for you.
Somebody should. All right. Before we run out of time. The blade has a path through the air like a corkscrew. But then I got to thinking about this analogy, and I thought, you guys are more of a wine in the box kind of a crowd. So,
Means you're cheap.
so I will say, or screw,
Helical.
a helical.
What if you don't drink
Helical. Beer
one?
bottle.
Now I will say this, even though it's on record. Maybe I shouldn't. Well, where I worked, one of the people that I worked with, I'll say it, she's a little more sophisticated than the rest of us and knows her wines, and the rest of us are not. And I think that we like to tease her about that. And so we had to unload a citation, Cessna citation, and get the wine off because it had to do weight and balance. And being of the more sophisticated mind, she had advised that the crew that was unloading the wine kept it out of direct sunlight. That way it wouldn't degrade the wine. And you have to assume somebody who can afford their own private jet probably did, in fact, have nice wine. And she was, in fact, correct. But being the group that we were, the guy standing there said, "That is why I only drink wine out of a box. Because I don't want the sunlight to degrade it, nor the light bulb that comes on in the refrigerator to ruin my vintage." To which she could only shake her head and say, "Why am I here?" Okay, so yes. So a corkscrew or a PK screw is what we have here. Why the two different representations?
Different pitch.
Different pitch. What kind of pitch is this? Is that fine or coarse? Fine. We have a coarse thread. So a propeller can be pitched to have a fine thread pitch where it takes more revolutions to go the same distance as this one over here, which only takes a few revolutions to go this distance. Well, if I stop and think about it, I think, well, if this one's turning at 2,000 RPM, this one's turning at 2,000 RPM, and this one's turning at 2,000 RPM, which one's going to go the fastest? Why wouldn't I just want that? Why would I ever want a fine thread pitch? For climbing, it's more efficient. Don't make me say plank again. So one of the problems with this one over here is if I have both of these aircraft on the ground and I do a static run-up, which one's going to have the higher RPM? Fine one, which means more horsepower. So anyway, I see it's time to go. So we will pick up where we left off.